Are you serious?
What?
It's working. You let that happen again?
No, it's good. I fixed it.
All right. Well, again, let's, or did you start recording?
Yep.
Okay, well, great then. Here we go. We're gonna go through Einstein developing special relativity. The whole point of this one is to be a little bit interesting about Einstein, but also to kind of show you something about the nature of physics, kind of a thing. All right, so, or the philosophy of physics. And what we're going to see is that we can have something that's extremely successful and it takes very little to topple it. All right, it does a whole lot, it does everything really well, you think you have everything figured out, and then, couple little issues pop up and suddenly you're in trouble. Now I'm going to do this a little different than I normally talk because I wrote out a bunch of notes for this so I can try and keep myself going on pace and get through this an hour. So we'll see. So it might be a lot of just reading what I wrote earlier now instead of just what I usually do, just jabbering off the top of my head. Okay? All right. So in 1905, Albert Einstein published a paper entitled On the Electrodynamics of Moving Bodies, where he first introduced the special theory of relativity. In this theory, Einstein presented two foundational postulates. The first postulate implies that absolute motion cannot be distinguished. Only the relative motion between bodies can be observed. For instance, an experiment conducted on a stationary train will yield the same results for an observer on that train as it would if the train were moving uniformly on a straight, smooth track. The second postulate emerged due to the perceived inconsistency between Newtonian mechanics and Maxwell's electrodynamics, and the Michelson-Morley experiment's inability to detect Earth's absolute motion. Unable to reconcile these discrepancies with the existing theories, Einstein formulated the foundation of his special theory of relativity. All right. You can make a comparison between the challenges faced in 19th century physics and the rise of Einstein's theory of relativity. So we're going to look at the parallels to it, and we're going to show that we had some redundancy in the Newtonian system. The origins of these challenges date back to the 17th century, when Leibniz and other natural philosophers critiqued Isaac Newton's concept of absolute space. Employing a purely logical critique, they nearly demonstrated that absolute positions and absolute motions were without any function at all in Newtonian's system. However, they couldn't identify a scenario in nature where the relativistic concept would deviate from Newton's absolute framework, leading their ideas to remain largely unaccepted. So basically, they logicked it out, but there was nothing that could show it was different, so there was no reason to adopt it, because it gave the same exact results always. The acceptance and evolution of the theory of light as a wave introduced challenges that would eventually be addressed by relativistic theories. During that period, it was believed that like mechanical waves, light waves needed a medium for propagation. So this came from some experiments that showed light acting in the wave. And if you're in my physics class, we were talking about that recently. Okay? This is where the concept of the luminiferous ether was proposed as the medium that permeates everything, and that's what light then would travel through. Right? Y'all have heard that you can't, no one can hear you scream in space thing they would put in old movies because there's no medium for the sound waves to travel through. So the idea was light can travel through space, there must be something for it to travel through. And I've already broken my rule of only reading because here I am going off. So, all right. Here we go, the luminiferous ether. This belief implied that even what appeared to be empty space must contain a medium for light to traverse. The proposed answer to this conundrum was the concept of a luminiferous ether, a mechanical medium permeating all of space, including vacuums, facilitating the propagation of light. cool, huh? Like the ocean, where the waves would travel through the ocean. This is something that goes all the way through there. All right. The attempts to detect the ether were unsuccessful. So, as a little example here, you can imagine if you're riding in a boat and you're looking at the waves coming off the front of the boat, they're all compressed and shorter looking than the waves coming off the back of the boat, correct? So the idea was that we should be able to detect something like that and figure out how we were moving through that ether. Yeah, this all was very unsuccessful and then led to a lot of very frustrated attempts to explain it theoretically. A lot of them were not good attempts, I guess I should say. They were kind of just hodgepodge together, make it work. All right, this spurred the development of theoretical explanation for the ability to detect the ether, even though these explanations often contradicted one another, so they were not very self-consistent or consistent with each other or with current theories. Yeah. Only in the late 19th century did James Clerk Maxwell's electromagnetic theory gain widespread acceptance. Maxwell posited that electromagnetism could somehow align with Newtonian mechanics, yet he struggled to establish this congruence. In the end, he excluded Newtonian mechanics from his definitive electromagnetic theory. And this is our idea of, you've probably ever heard that light is an electromagnetic wave. That's what Maxwell did with his theory of electromagnetics, is he showed that it was like, you could have a wave from it that had all the properties of light. So that's where we get that. And so this brought in the physics crisis. The endorsement of Maxwell's theory, coupled with previous failures to detect the ether, precipitated a crisis in physics that couldn't be addressed by Newtonian mechanics. So this is bad. Things weren't going well. In the 19th century's final decade, renewed efforts were made to experimentally identify the ether and theoretically rectify this inconsistency. Efforts to identify the ether persistently failed, despite the promising contributions of Lorentz and Fitzgerald. The theoretical solutions remained unsatisfactory. This continued state of crisis set the stage for Einstein to introduce his special theory of relativity in 1905. You doing okay so far? Not falling asleep yet? Okay. In 1946, Einstein recalled a thought experiment he had first contemplated at the age of 16. At least he said he thought of it when he was 16, so I guess we just kind of trust him on that. In this thought experiment, Einstein envisioned what it might be like to journey alongside a light beam while moving at the speed of light. This scenario would present a, quote, frozen light wave. So that's what you imagine. You run right along it, and it would appear like it was just sitting there. And this was a lot of trouble for him to understand what that could possibly mean. So he ultimately decided that this was an impossibility, given that neither experience nor Maxwell's equations provided a theoretical basis for such an occurrence. From the perspective of an ether scientist, Einstein's reservations about the frozen light wave don't seem all that bad, pointing out that Maxwell's equations do not inherently conflict with this frozen light wave. But we tend to take the stance that Einstein just had a better insight to this than the rest of us, and even though we don't understand exactly why he felt this was impossible, he probably was just a much more profound understanding than we have, and therefore he was correct, because it kind of turns out that way. Okay. Einstein progressed beyond his initial reflections, delving into more intricate thought experiments, particularly focusing on Maxwell's electrodynamics and motion within that framework. Initially, Einstein conceived experiments to detect motion relative to the ether. However, he eventually chose to discard the concept of an ether altogether. So even he himself initially tried to make this ether thing work. All right? In the introduction to his 1905 paper, Einstein describes what seems to be the pivotal thought experiment that led him to wholeheartedly adopt the principle of relativity. In this experiment, he leverages Maxwell's electrodynamics prediction. A moving magnet generates an electric field, whereas a stationary one does not. This could offer a straightforward method to test for absolute motion relative to the ether, but it doesn't. It's ineffective, doesn't work. Okay, and you can see that kind of here in the picture. Basically, attempts to detect this electric field are fruitless. The detection method would involve placing a coil of wires near a magnet, then observing any current induced by the electric field resulting from the magnet's motion. Yet theory suggests that another current induced by the magnet's motion would precisely negate the current produced by the electric field. Consequently, the outcome, no detected current, remains consistent whether the magnet is stationary and not generating an electric field, or in motion, producing both the electric field and its counteracting current. So basically what we're saying here is, if you move a magnet, it creates an electric field. This electric field can then be used to generate electricity in a coil of wires. In fact, this is pretty much how all of our electricity is generated, from the alternators in your car to big giant, the Hoover Dam, nuclear powered things. Ultimately, the idea is move a big magnet near a stationary coil of wires and get it to create current and therefore get electricity going. But in what he is talking about here is, if you have these things moving and they're moving together, that whether you look at it as the idea that it's not moving and the coil's not moving, they're just sitting there, in which case no current is made, but rather take them both and move them, in which case you'd say that magnet is now making an electric field and therefore there should be current in it. That motion also produces the exact counterpart, which means you get absolutely no current anyway. So the moving version of this and the stationary version of this, are identical. Okay? And that's kind of a big point here, is that they are identical, and therefore you can't tell anything. It makes no difference. All right? So this conundrum seemingly prompted Einstein to forgo the ether concept. It also underscored the notion that the presence of an electric field around a moving magnet hinges on the relative motion of the observer, attempting to detect said field. It is actually it's a very classic question where, if you're learning this subject ever, to have two electrons that are moving like this, if they're moving past you and they're right next to each other, you can account for their motion where they're split apart like that just by magnetism. If you're moving with them, so you're going along with them, so to you they seem like they're not moving, they still spread apart. It's just that their motion to you now is exactly accounted for by the electric field. If that makes any kind of sense, you don't have to involve the magnetic field. So depending on whether or not you're moving relative to them or not, determines whether or not you see an electric field or a magnetic field. And then depending upon whether you're moving or not, switches the result of how you see it. Like if I'm sitting still, they look like they're curving away from each other. And if I'm moving with them, they look like they're just moving straight apart because I'm moving with them. You just get the exact same results either way. This kind of actually brings on the idea that we don't really have magnetic fields, that they're just a relativistic effect of electric fields. So magnets, they're just moving electric fields, kind of an idea. In fact, if you apply Einstein's relativity to electricity and magnetism, you can just remove magnetism entirely and get all the exact same results with just electrical fields and this relativity stuff. Einstein then endeavored to formulate an emissive emission theory of light. He examined Maxwell's prediction of electromagnetic waves that traveled at the same speed as the observed speed of light, leading to the inference that light is an electromagnetic wave, which I mentioned a little bit earlier. This predicted speed remained constant, irrespective of the motion of the light source relative to the proposed ether. This consistency again suggested a method to detect the ether. Yay, trying to detect it again. All right, by measuring the speed of light, any deviation from the predicted value would indicate motion relative to the ether. Attempts to detect this, what do you think? Failed. They failed. So essentially we're at this point where we just can't detect a change in the difference in the speed of light in any situation. And that's one thing. It's not a huge bunch of things, and it suddenly is something we just cannot explain, and that our previous theories that work so nicely together suddenly don't explain it for us, and they don't work. All right, to uphold relativity, Einstein revisited a Newtonian perspective on light, which considered the velocity of light, of the light source, in addition to the velocity of the light itself. Although this approach would negate the potential to measure varying speeds of light based on motion relative to the ether, it proved challenging to integrate into Maxwell's intricate theory. Ultimately, Einstein encountered numerous issues with this method and discarded it. So, as you can see, he's tried a few things and been unsuccessful. It's not like he just came out the first time and said, hey, I have this brilliant idea and it worked. You know, he spent a long time thinking about this and working on this, and before he ever, you know, came up with something that was good for it. The shortcomings of the emission theory left Einstein grappling with a conundrum. The speed of light remains unaffected by its source's velocity, and the electrodynamic theory must adhere to relativity. So let's think about what we're talking about with this speed of light has to adhere to or be independent of its source's velocity. So let's say you could throw a baseball at 50 miles per hour, okay? And if you're just standing there, you throw the baseball as hard as you can, it goes 50 miles per hour. But now let's say we put you inside a train car, and that train is traveling at 50 miles per hour. And then you throw that baseball in the same direction that the train is going. How fast is that baseball going to go to someone standing on the side of the tracks? 100, right? It's going to go 100 to them. To you, it goes out 50 in front of you, but to them, it'll appear like it's going 100. It's the 50 of the train that the ball was already going, and then the 50 that you added onto it by throwing it. All right, and if you turned around and threw it the other way, you'd be throwing it 50, and the train was going 50 this way. What would it do to if someone was standing on the side? Just zero. It looked like it just fell to the ground. And you can probably find YouTube videos of this experiment and show where they like fire something off backwards. If something moving this way, they fire it backwards at the exact same time. It does. It looks like it just falls straight down. Okay? So that's the idea of going on here. But that didn't seem to be happening with light. It seemed like if you were on a train and you had your flashlight and you shined it forward and you measured the speed of light, right? A person standing on the side here watching you, they wouldn't get the speed of light plus the 50 miles per hour of the train. They would just get the same exact speed of light that you did while you were on the train. So that motion just was having absolutely no impact on it. So this led to the introduction of the concept of relative simultaneity. To address this, Einstein began to reevaluate the notion of absolute simultaneity. Simultaneous events are simultaneous for all observers. So if you see two things happen at the same time, everybody thinks they happen at the same time. Introducing the concept of relative simultaneity, events that are simultaneous to one observer, but not necessarily to another. All right, that's what he did instead. So you can see here in this picture, we have the idea of two lightning bolts striking those two lightning rods on either side in the top picture. And then what I have is just the little sphere of light of the vision of seeing the light spread out, after it hit there, it creates light and it goes out. Now, if we just stood right in the center, as you can see, I have a little person there, right? See the little person? Standing right in the center, the blue person, both the lights from both of those will reach your eyes at the same time. And you would say then that the lightning rods got struck at the exact same time. But if you look at the person in red who is moving to the right, what happens here? He sees the one on the right first. And then it's not till he moves further away that he sees then the one on the left. He would say that the two lightning strikes did not occur at the same time. So the question is, well, who is right? Well, so far we can't tell absolute motion, so can we really say the guy in red is moving and the guy in blue is stationary? I mean, maybe Earth's rotating that way and the guy in blue is rotating with it and the guy in red is moving the exact speed that Earth is rotating in the opposite direction it's rotating, so he's like the one that's actually stationary, like running on a treadmill. Right? So who do we say is correct here? That becomes a big issue because they disagree. They disagree and we have no way to tell which one is right. So that's where Einstein introduces this idea of relative simultaneity, when they don't necessarily have to agree. Okay? He delved into various philosophical works and discovered a prevailing sentiment. Concepts are our servants, not our masters, and they are warranted only insofar as they might be grounded in experience. What do you think he meant there? Or what he found out there? You can have, think of string theory. Y'all ever heard of that? String theory? Yeah, it's beautiful mathematically. It's very internally self-consistent, but it doesn't match reality. So it has to be grounded in experience. You can't have it be just something that looks good but doesn't work that great. All right, with this perspective, Einstein discerned that the principles of relativity and the constant speed of light could coexist harmoniously. Moreover, this congruence demanded no alteration to Maxwell's electrodynamics. So that idea of people not having to witness the same events the same way helped a lot. Okay? There's even actually some classic problem I used to do with my students where from one perspective, you saw like a spaceship fire its laser beam, and then you saw this planet blow up, but from another perspective, the planet blew up, then the laser beam was fired, and it was like, how do we know then, were they the ones that blew up the planet and attacked it or not? There are answers to that. There are ways you can actually get around that. It's called the space-time interval. But so we disagree on this, but eventually it comes back to him figuring out things we can agree on. Okay, even though we disagree on these other things, we can kind of mix them together in a way and come up with an idea to agree on, and therefore tell what each other would have seen. All right, special relativity has undergone rigorous testing and has proven to be highly accurate under the appropriate conditions, leading to its widespread acceptance among physicists. However, special relativity does encounter limitations in specific scenarios, such as in non-inertial frames in the presence of intense local gravitational forces, or when measurements reach or dip below the Planck length. So what I mean by those three things, non-inertial frames, that means it's accelerating, speeding up, slowing down, or turning. This theory doesn't account for that. It's Einstein's general theory of relativity that he publishes 10 years after this that accounts for those situations, which also then, as it would turn out, accounts for the gravitational forces stuff. So general relativity takes care of the non-inertial frames and the gravitational forces. He actually combines those together into what is called his equivalence principle. Another brilliant thing he did. And then the Planck length, I mean, actually pretty much nothing we have in physics works below the Planck length, because it's like the length where if you put any two things down at that length, they automatically like turn into a black hole, basically. we cannot do any physics below that so far with any of our theories, so that one doesn't work. It's really close. I think it's 10 to the negative 35th meters, which we can't get anywhere near measuring that small at the moment. I think we can get down to like 10 to the negative 18th meter, so we're not anywhere near. Okay. For situations dominated by strong gravitational fields, general relativity becomes the go-to framework. In low gravity contexts, general relativity reverts to special relativity, and thus special relativity is viewed as an approximation for general relativity in its applicable situations, which is low gravity inertial frames. So it works really well, but if you get into high gravities, like special relativity works really well around this planet because we are not a high gravity situation. It's used in all sorts of manners and works, but if you're getting near like a black hole or something, it doesn't work as well, and you have to go to the much more mathematically difficult general relativity. And when I say much more, I mean much, much, much more difficult.
Sorry, not bothering you, but I forgot everything, so I couldn't get anything. Would you explain what is difference between Maxwell's and Newtonians? So Einstein followed under the Maxwell theory.
Well, let's get to that at the end. Let me get back to you on that one. I have some like discussion questions at the end.
Sorry.
It's okay.
From
It's
the
okay.
first time I forgot, I couldn't get anything. So.
That's okay. This, yeah, anyway. We'll just keep trucking through it and then we'll get to the discussion things. All right, special relativity has undergone rigorous testing and has proven to be highly accurate under the appropriate conditions, leading to its widespread acceptance among physicists. However, special relativity does encounter limitations in specific scenarios. Didn't I already just go through all this? Oh, no, I didn't. So, there's where it goes. At extremely minute scales, quantum effects. This is what happens when Dr. Kim interrupts you. You get off of where you were talking. Yeah. At extremely minute scales, quantum effects come into play, giving rise to the concept of quantum gravity. Within the realm of quantum gravity, it's noteworthy that out of the 4 primary forces in nature, 3 of these, the electromagnetic interaction, the strong force, and the weak force, can be explained using quantum mechanics and quantum field theory. Only gravity remains outside of that, of this framework, and is not even close to being integrated into it. So there is that possibility that gravity just is not quantum mechanical and will never be explained by it. So, who knows? All right. So since its introduction, numerous scientists have applied special relativity to a variety of scenarios, illuminating many of its implications. Some notable outcomes include the Thomas rotation, which is the perceived rotation of an object when observed from a moving frame. So the idea basically is it actually kind of makes things rotate. So if you had a box sitting right in front of you and you couldn't see this side of the box, if you started moving with it and you were both moving really, really fast, you would actually start to be able to see that side of the box. It would rotate. It would appear to rotate to you. And you could see the side, the side that was normally out of view for you. Yeah. The light clock, which is a very big one, consisting of 2 mirrors that reflect light between them to track time's passage, which we'll look at in the next slide a little bit more. And the twin paradox, which highlights the age disparity between twins moving in distinct reference frames resulting from time dilation, which we're about to talk about. Hermann Minkowski's work was pivotal in refining the theory. In 1907, Minkowski introduced his papers on space-time, leading to the concept now recognized as Minkowski space. This offers a geometrical interpretation of relativistic mechanics, merging time and space into a unified 4-dimensional space-time, in contrast to Newtonian mechanics, where the time operates independently from 3-dimensional space. So he clumped it all together into one space. All right, not just X, Y, Z, and then there's time, but all of them together. So for example, if I said meet me on the corner of this street and this avenue on the 3rd floor of this building. Would you be able to meet me there? What if I left out?
Assuming we agree on time.
Yeah, when, right? Are we meeting in an hour? Are we meeting in 6 years? When are we meeting, right? So the idea was that time was a big part of space, and so it got lumped together into this thing called space-time. In fact, it was called Minkowski space now a lot of times, which later gets expanded on. So let's take a look at the light clock. So the idea of the light clock is that if you want to measure the amount of time that occurs, which by the way, if anybody ever gets interested in this, it's really wonky. It's because the way you measure distance is by measuring how long it takes to go someplace and back, usually with light because it's the consistent thing. But the way you measure the speed of light is by measuring how far away it had to go and come back. Yeah. So one of the questions arises like, can we really actually measure time or distance or anything like that? It's very, very complicated. So anyway, but keeping it simple, the idea is you have these 2 mirrors, you have a stationary one, you send one light ray up, it hits the other mirror and bounces back down. Now, the thing that occurs here is if you have this light clock moving, so say we put it on a train, and you're watching the light bounce back up and down. Well, if you're on the train, this is the scenario you see. And the light going at a certain speed goes up, say 1 meter, which is gonna make up some easy number, then come back down a meter, and you're like, okay, it took 2 seconds, or whatever it was, right? It took 2 units of time. But for someone standing on the side, they see the light go up at an angle, right? So instead of this, they see this, right? And so they see it go up at an angle and come back down, which is the hypotenuse of a triangle that is greater than the distance that it would have gone just straight up and straight back down. So the light travels a greater distance. But through all of our experimentation and everything, we found that no matter what, the person on the side of the train and the person on the train both see the light going at the same speed. But in the same exact event, they saw the light travel 2 different distances at the same speed. So if it has to be the same speed, and it has to be 2 different distances, then what's the thing that has to be different between the 2 of them? How long it actually took. So for this guy, with up 1 and back down 1, he counts 2. This guy counts like 1.5 up and 1.5 back down. He's getting a 3. So this guy thinks 2 units of time went by. This guy thinks 3 did. For the exact same 2 events. And this is that idea of time dilation, that if you get things moving differently, their times run differently. This has been experimentally shown so many times, probably more times than anything else ever has been done, has been verified. In fact, every time you use anything that GPS is your location, it's using this. The GPS system only works because it takes into account this shifting time for the moving satellites, because it's basically just a giant time system for GPS. And so if it finds your location accurately, it did it based on this and verified it. And you could imagine every phone, every GPS unit, all these things that have that, and they update your location sometimes, especially if you're using it every couple of seconds, every 3 or 4 seconds, every 10 seconds, something like that. And now everybody on the planet with one of those phones or one of those GPS devices doing this all the time, and every time it's telling them accurately where they are, is a verification. I can't think of any other scientific experiment that has more verification than that, right? Billions upon billions upon billions of times this is getting verified daily, right? So, okay, anyway. Yeah, so in a moving light clock, the light appears to travel further than it does from the stationary perspective. The speed of light being invariant, meaning it doesn't change, implies that the stationary perspective will find a shorter amount of time passage than the moving perspective. During this 1 tick of the time clock, moving clocks appear to tick more slowly. Yeah, experimental testing of this. Numerous experiments have been designed to test the predictions of this. Every once in a while, something doesn't work out. Most recently was that those people at CERN with the big giant collider that thought they found faster than light moving neutrinos a few years back, and turned out to have been their mistake. So pretty much every time anybody comes along and says they think they have found a flaw in Einstein's theory, it's their mistake. No one has yet to actually have a good flaw in it. Okay, so in addition to theoretical contributions, numerous experiments have been devised and executed to test the predictions of special relativity. A few have exhibited discrepancies with the theory, but these inconsistencies have not been replicable. So they were mistakes, implying that the discrepancies probably arose from instrumentation errors like the faster than light neutrino from 2011. Did y'all ever remember that? Were you old enough for that when that happened?
What year?
And they announced it, and it was like this big thing. They thought, and then it turned out it was.
Mm.
Well, they claimed it was instrumentation error, but some people think they just did the math wrong. There was a guy who published who sent them like a letter, only referencing Einstein's original 1905 special relativity paper, and completely accounted for their mistake, saying that they did this wrong. And then it was very shortly after that they retracted and said, "Oh, we had a mechanical issue. We had a equipment malfunction." So who knows what it really was, but all right. Conversely, a significant number of experiments, both contemporary ones such as time dilation, observed through high-speed muons, and those predating Einstein's theory, like the original Michelson-Morley experiment, are deemed confirmatory of special relativity. Many cutting-edge technologies, including particle colliders and the Global Positioning System, GPS, rely on the principles of relativity for their functionality, which further validates them. The muon thing is that there are these muons that get created. They're a kind of particle, heavy particle. They get created in the upper part of the atmosphere, and they decay so fast that based on how fast they fall, they should never reach the surface of Earth. But because it takes them like a half a second to get down here, but they decay in a tenth of a second. All right, so if you look at how fast they fall and how fast they decay, you should never detect them. But if you had a muon detector and you walked outside right now, you could detect them. And the idea is that from our perspective, they are moving so fast that their clocks slow down. And so what we see as a half a second from the fall, they see as way less than that amount of time to fall. And from their perspective, what they see as, we see as they have to fall this distance. From their perspective, we have something else that comes relative, and that's length. They think they only have to fall this distance, so they think they make it too, because the distance they have to fall looks compressed to them, which kind of goes along with that whole rotation thing we're talking about. All right. Special relativity also serves as foundational requirement in specific physics domains. For instance, the initial formulation of quantum mechanics using Schrödinger's equation did not incorporate special relativity. Its subsequent inclusion gave rise to a new branch of quantum physics called quantum field theory. Among the most prominent is the first quantum field theory introduced by Paul Dirac between 1927 and 1928. Y'all don't care about that, do you? Yeah, it's been getting refined ever since then with the inclusion of that. Quantum field theory, it's probably the most accurate theory we have as far as it predicts out to so many decimal places with good accuracy. But that's a whole nother talk. All right, with Einstein's special relativity, we have seen that a new scientific model can surpass the current model in accuracy. This is evident in the theory's ability to converge with the precise predictions of Newtonian mechanics in low-speed scenarios, and its explanatory power regarding the failed attempts to detect the ether. As emphasized, this theory aligns consistently with both historical and subsequent data, matching or surpassing the accuracy of theories that were in place when it was developed. So it didn't take a lot. It took a lot to come up with the other answer, but as far as the total problems that were there wasn't a lot of them for such a huge amount of changing ideas in physics to occur. So I have some discussion questions if we wanted to do those. That's up to y'all. But I did want to come back to what you were asking. The big problem was that, Newtonian mechanics predicted the speed of the light and everything, the speed of things would be additive. Like I was talking about with the train when you threw the baseball. So if you throw it at 50 and you're on the train going 50, you would have 100. But Maxwell's did not predict that. That's where they were disagreeing. And so that's where we thought we should be able to find it in the ether. And so Einstein's the one that came along and said, oh, well, guess what? We actually can put them together, and that was his special relativity along with the Lorentz transformations. But I didn't talk about those because I was trying to do no math. Is that okay?
Okay.
Do we want to try the discussion questions? No? Maybe?
If you move same direction, then field zero. Baseball and train move in same direction, then speed if your speed is zero, the opposite direction is double, isn't it?
If you throw the baseball in the opposite direction of the train and you throw it at the same speed of the train, then it appears to have a zero speed if you're on the side of the train. It appears to just drop straight down. But if you were on a train that was going the speed of light, which Newtonian mechanics does not prohibit, and you shined a light backwards, it still would travel out and go backwards. It wouldn't just stay frozen right there in the air, which is what Einstein was talking about. He was saying with that whole frozen wave thing, if you were to go running alongside a wavelength of light, it would appear to just be frozen, which according to him somehow was just not possible. Which, I mean, I can't think of what that would even mean physically. Like, I think one of the things he talked about was like if you were looking at a mirror and holding it in front of your face and you kept speeding up and speeding up and speeding up, what would happen to your view of yourself in the mirror if you hit the speed of light? Because at that point you'd be going the same speed as the light coming off of you, so it would never reach the mirror to back bounce and be able to see yourself.
Speed of light is a constant speed?
As far as we know, yes. In a vacuum. If you put it inside another material, there's interactions with the material that don't really alter the speed of light, but they cause its overall propagation to be reduced. Because you could almost think of it like if you had to run through, like instead of being able to run straight through like you can in a vacuum, it had to zigzag all the way through. It suddenly slows it down. The models that explain that a little better now are a little more complicated than that, but that's a decent idea to think of it as. So yes, in a vacuum, we cannot, so there was the Michelson-Morley experiment, which maybe I should have added something in here a little bit more about that. But the idea was, as Earth moved around the sun, right, we would be moving through that ether, like the boat moving through water. Now, if the boat is moving through water and you look at the waves coming off the front, they're short and compressed. The waves coming off the back are long and stretched out. There's a difference. And so even if you have if you're stationary to the boat, you can tell which way the boat's going in the water because you can look at the waves. And they're different, coming off the front versus coming off the back. The idea was, as Earth orbited, we should be able to point light in the direction that it was going and measure one wavelength and one speed, and then point it in the opposite direction and measure something different. But that did not happen. No matter what way they pointed light, no matter what they tried to do, it was always coming out the same. So that was experimentally done. And then this was not able to be rectified between the two theories. Einstein's special relativity replaces Newtonian mechanics with relativistic mechanics using the Lorentz transformations, and it actually predicts both what we see here at low speeds, which is like the 50 mile per hour baseball plus the 50 mile per hour baseball. It's a slightly different vector addition, so it's not exactly 100, but it's so close to 100 that we can't tell the difference at these low speeds. But at very high speeds, the vector addition changes, and it becomes much more apparent and accounts for this difference. Y'all didn't seem too excited about the discussion questions, so I guess we can kind of skip that. Any questions at all? Yeah.
How does Einstein's theory explain light traveling? Does it just assume it's not a wave then?
No. It never says it's not a wave. It just says it's not a mechanical wave.
Oh, okay.
So at the time, it was all the waves that we knew were mechanical waves, and all mechanical waves require a medium. Light, however, since it doesn't seem to require a medium, or at least there's no reason to ever include one because it doesn't add anything, doesn't change any predictions or anything like that. Nothing changes by its inclusion. Instead, it just makes it very complicated because you have to then account for why it's not detectable. We don't consider light a mechanical wave. It's a totally different kind of wave. You might want to go back and look at my last talk on the reflection of light,
Yeah, I remember.
where we talked about it being like a probability kind
Yeah,
of wave.
no, I remember
of
that. I
appearances.
remember that. Yeah.
So it's not a mechanical wave.
Sure.
It's more. Honestly, I wouldn't even call it a physical wave. It's like a almost a probability abstract mathematical idea of a wave.
Yeah. No, I understand that.
So-
No, I just didn't know if there was just something. Yeah,
Nope. Pretty much it. Anything else? I know there's, don't put your hands up all at once, we'll get to everybody.
It was a lot of trial and error. Like,
Huh?
Like it was a lot of trial and error.
Science, it's always trial and error. The basic idea is you look at something, you observe it, right? So and then you make some sort of correlation where you say, every time A happens, B happens. And then you try to come up with a model that explains, well, if A happens, then B happens, we think that A causes B. And then we come up with some sort of model that explains why A causes B. And then you do it a whole bunch of times. And A keeps causing B. So then you're like, well, if A really does cause B because of this, then if we do this with A, it should cause C. So then you try that with A, and you see if you get C. If you get C, you're like, good, that's confirmation. If you don't get C, you're like, great, let me go back to my model and readjust, or try and figure out why I didn't get C, because maybe I messed up something in my interpretation of the model. So you either adjust the model, or you come up with a new model. Usually we spend a long time just adjusting the models. But every once in a while, someone comes along that just comes up with a new model that just kind of blows everything away. Yep.
Going off of your discussion questions, do you foresee anything coming as a replacement or anything like that?
Me, myself, if I did, I would sure go publish it right now. I mean, it's been over 100 years, and I don't know. I don't know everything. I am obviously not that smart. So on one hand, I like to always say that in 100 years, people are gonna look at us and be like, oh, can you believe they thought this? And it's like about all our science theories, and they'll all have been disproven, and there'll all be something new in its place. I just don't know. I really don't know. That's why I put that one in there. I really just don't know. I have no idea. It might be just the way the universe is, at least as far as we can measure it, and so this is a good model. Or there might be a better way that someone comes along. I mean, I guess general relativity kind of replaces it. But will something replace general relativity? Every time they come up with something in quantum, they're like, look, we confirmed quantum. Everything must be quantum, and so on. Then, inevitably, shortly after another, prediction of general relativity, then they're like, look how accurate general relativity is right here. Look at this. Look at how we took a picture of a black hole, and look how accurate general relativity was. And it's kind of like, okay, which one's going to win out here? I don't know. We haven't been able to piece them together. So maybe there is something that'll piece them together. Maybe it'll turn out they're both so horribly wrong that we'll find all this stuff in the future that neither one of them predicted. We'll have to have totally different theories and models because they just totally stop working in lots of new situations that we find. And I mean, that's kind of the point of this, right? Tomorrow, someone could find something that none of us can explain, and everybody's gonna try and make it work. And they're gonna try to make it fit, and they're gonna try to save this. And if they can't, eventually somebody else is gonna come along that's gonna offer a new idea that works with it, and then there's gonna be a bunch of fighting, and then there's gonna be a big shift, because the old people that were stuck on the old stuff will go away, and the new people will come in and they'll replace it with this new theory, and that'll be the new thing, and it'll be a big revolution. Which is what happened with Einstein's stuff, with the relativity and the quantum mechanics, replacing all that old stuff. Anything else? Okay. stop it.